a small introduction, but before we start, I'm going to first show the Goonies project we are working on. This was actually
and now for the PowerPoint. Again with that logo. Good afternoon. Let me first introduce ourselves. This is Stephan, and it's actually taken in Barcelona 2 years ago on another DEVCON. And my name is Maarten Loor. There's 2 more members of NOP, which are not present today, so let's introduce them. That's my brother Wietse. And our friend Mark, who lives in Switzerland. But let them ignore for a moment because they're not here. So let's tell you about the start of NOP when we started out with the first project. This is at home at my place. When we were still working on Unknown Reality. And this is actually the day that Unknown Reality was presented on the fair in the Netherlands at night. And Stephan was still working on it. And this is, I think, in Tilburg in the Netherlands, one of the fairs in the early days when we started out, selling more games, and it was a really big room, sport complex with a lot of people in there. This is Bart Roymans making fun of us, and he did the music for Unknown Reality. This is, I think, in Zandvoort. It's another place, the other fair, and I think in '95. So you could say we started out in '94 actually. We did some things that we didn't release before, and the name NOP was not known at that point, so let's take a look at the portfolio. So what did we make in all these years? And you might recognize some of them, and you might not, I don't know. But they're all downloadable now from our website, and we don't want to talk about the one at the bottom in the middle, which was never finished. So what are we going to do today at the DEVCON? Now we're going to show you a peek in what we do and how we did it. And you could say it's our TED Talk. So I have 5 different topics today. One of them is the compiler we are using to compile our products. The PSG Samples project, which Stephan will take the first 2 topics. Then we'll do some explanation about the melon in Unknown Reality, and 2 topics of sales Discontinued. Now I'll turn the mic to Stephan, who will tell you about the compiler. Stephan?
Thank you. Well, the compiler we use in our current development projects provides us with some flexibility we require. It does a lot of default plumbing, and it's also customizable. The next topic we'll talk about such customization, the PSG Samples. But first, we're going to show some code, and you can see several keywords. For example, we have the keyword namespace. And namespace is to group parts of code, and it also avoids naming collisions. Then we have keyword vars. That's, for example, used if you create a ROM, then you cannot put, of course, variables inside ROM, so the compiler detects this and it puts those variables in an area where there is RAM located. Of course, you see here a call F statement, and that's a command we introduced to call var calls. So what you see here is an Z80 memory layout, and you have also the ROM cartridge. And if you have a program like this, it calls the game intro code. It is located in a different segment. So what the code does is it calls a helper function. And this helper function is actually located in the top area of the memory layout. And the program calls that helper function. That helper function selects a different segment. It calls the game intro. It does its thing. Then it returns. And the program is reselected. And we're back in the program. So normally you have to do that by yourself, but now the compiler does it for us. Here we have a keyword that declares where the code is, and it compiles it, and it puts it somewhere in the ROM, the best way possible, mixed with all the other segments, so you don't have to calculate and know where you put your code. The compiler does it for you. And of course, each game is having code, but also some data. For example, in the Goonies game, we have some data that is indicating how we need to shape the screen. And we put the keyword data on it. And we set a parameter called language to C#. And we can add a small program that outputs the way the screen has to shape. Over here you see where the output is generated and returned back to the compiler. And this syntax is very similar to the classic ASP that Microsoft used way back. Of course, in the Goonies game, we have data in terms of a sample, and those samples are generated by an external program, so that's also possible, like this. And then we have extension methods, and that's just an easy way to write code. It's more, smaller. And then we're going to talk about customization of the compiler to play actual samples. So the samples we did is the M61, play the Goonies game. So how are samples generated using only the PSG? Well, PSG has 3 samples, and the output of the individual channels has 16 steps. But thanks to its logarithmic output scale, it's possible to make more steps when we combine channels together. For example, when we combine the following 3 outputs, and we add them together, we get an output of 0.3. That corresponds with an 8-bit sample of 79. Sound obviously contains of multiple samples, so let's do a quick example for another sample. Let's take the 8-bit value of 192, and that corresponds with a output value of 0.75. What channels do we need to add to get to that value? Well, we could do a half, and we could add a quarter, and 0. So, just look at the slide for a moment. The difficult part is if we apply the new sample with a half, then we get a output result that's a combination of the previous sample with the new one. So we get a temporarily distorted signal, 203. When we apply the second channel, we get another distorted signal, 255. We set the last sample value, we get our final result of 902. And these two folks, they discovered a way to minimize that distortion by carefully selecting the right combinations between consecutive samples to minimize the distortion. So, now we're going to talk about playing the samples in the code. And the only way possible to play samples on the MSX with a Z80 that isn't that fast is to write code for the game and also code to play samples. And we interleave those two together. Like this. So if you have a program, for example, with this keywords, these commands, a lot more, then we need to add inside that code, at some point, a play sample command. And of course, the frequency of the sound is, if it's high, then you need to play a lot of samples. If the frequency is low, then you can do less samples and more code. So it's a little bit a trade-off between good sound quality and CPU time you have left over to do other things.
Let's compare playing samples with walking to get an idea how the compiler generates the code for playing samples. An analogy. Code flow is the same as walking. An instruction is the same as a footstep. Playing a sample is the same as drinking water. And good sound quality is the same as staying healthy. Let's take a look at the map of Pisa. This map isn't that very clear, so let's change it into a map of a place that we're all familiar with. The compiler puts a lot of healthy drinking points along the route. We walk and we drink. We play a sample. Let's start walking to the first drinking point. We drink and we play a sample. Let's resume a walk to the second drinking point. Again, we drink and we play a sample. And we continue to the third drinking point. We drink and we play a sample. And this goes all the way to the end. But code doesn't run in a linear way. It's like when a penguin is taking a detour. Now it's getting into a loop. With no drinking points inside this loop, we are not staying healthy, we are not playing samples. With static code analysis, the compiler detects this situation and adds an extra drinking point inside the loop. Now the loop is broken, we're drinking water and we're playing samples. Furthermore, the compiler moves the other drinking point a little bit further. Let's take a closer look at the drinking points. 2 drinking points are spaced accordingly to the applicable sample frequency. However, their distance could vary a little bit. Sometimes the distance is too large. Sometimes it's too short. Well, that isn't really the biggest problem, as long as we keep the average distance of all drinking points correct. The biggest problem is when we take a turn when we walk the ice of the Arctic and we walk into a drinking point way before we should be, according to the specified distance. And this is a hard part to solve, especially since we eventually have to implement this all in code. For that, we need to find a solution. We need to start thinking outside the box and hope for that one crazy idea to make this work. Okay, this could work. Instead of always drink when we run into a drinking point, we're gonna skip the drinking and we're only gonna do that when we're actually thirsty. And that's the same as we're only gonna play a sample when it's needed. The distance we have walked
is the same as the number of instructions we've executed. The walk speed equals to the time an individual instruction takes. And these two together, if you divide those two, then you get a unit of time. And the same goes for this part. And you could say the walk speed you are walking is a constant. Does it also apply for code? Well, obviously not. But with a little trick, by adding dummy instructions, we are able to get this one also a constant. So eventually, those two doesn't matter. We only have these two left. We only play a sample when it's needed, and instructions executed. And this is actually an instruction counter. Do we have an instruction counter on the MSX? Yes, we have. If we take a look at the Z80 registers, you can see here register R. Register R is an instruction counter.
It's actually used for mounting the flash, but you can also use it as a D-state counter.
Yeah, that's correct. The register was introduced to make sure that your RAM doesn't get corrupt. So what we do is we read the number of instructions executed, and we check that number with a specific number. And if it's greater, then we play a sample and we reset the instruction count. And we are counting from 0 to a specific number. That number is low when the frequency is also low. And that number is, I say it differently, that number is great when the frequency is low, and also the opposite.
The implementation in code looks like this. We load A with register R. We check if we counted all the way up to 64. In this case, we are counting from 64
minus that number all the way to 64. And then we play a sample, we update the PSG registers, and then the cycle is complete. So that's the part of playing samples in a game. And I'm going to hand over the mic to Maarten to talk about the next 3 blocks.
AKA the fun part. Did everybody understand this? No! Okay. You can talk to Stephan afterwards and get more details or look at code. But let's now go a step back into the past. That was a non-reality. So, does anybody recognize this? Also not? Okay, great. But it's an MSX2 demo, right? This is done on the MSX2. So how did we do it actually? Let's take a look. So I start out with a pyramid. Yes, a pyramid will become a ball. And I'm using, we were using 2 registers, main registers from the VDP, which is 23, which is the display offset register, and also 19, which has a bit for the interrupt line register. So what basically we did is, if you look at the pyramid, which is in VRAM, and I have the display on your screen, I can take this line and display it at the first line. So it used to be on like 10 or so, or 8 actually, it's not right next to it. So if I do that multiple times, I get ball. That is great. But what about the rotation? Well, I'm not sure if you guys actually program, but if you program, you probably will recognize the color loop when you see it. So let's make it easier, because we use 16 colors, but in effect, on this example on the screen, it's just 4 colors. And if I move the blue one to the purple one, and the purple one to the red one, and so forth, I can see it's already moving. So now let's change it to be the same colors. But you still will be seeing that I'm using 4 colors, but they will be displayed as shades of green. And I can do the same trick, and then it moves. And then you have this. So it's basically displaying other lines of that pyramid all the time. Did you guys like that?
Yeah.
Yeah. But that's not the only place we... Yeah, thank you very much. And we didn't use that trick once. So let's look at this one. You might also recognize it. It's the same trick. It's the same trick, but with a twist, actually. So on the left you can see what's in the VRAM, which has a scroll in there and some, again, pyramids. And on the right you will actually see what is displayed. And this is what we call a horizontal screen split, which does not really exist. But if you start at the line on the left and you wait a little bit with instructions and then you switch stuff over, you can display like line 10 on the left, but line 40 on the right. And that is what it is. That's all what it only did. So this is a vertical screen split still, and this is also a vertical screen split, but it's a different one. That's it. So let's move on to some current time. So 2 years ago, we have this game. You will also recognize it. But as I've heard that not all of you guys have the hardware to run it. Yeah, too bad. but I still talk about the scene design in here. So let's take a step back. Where are the graphics coming from? Does anybody know? No?
Oh.
It's American Dad and Family Guy, which has combined more than 50 seasons of graphics. Name any scene and it's probably already made. So what I did is go through that footage and take some graphics and then modify it to fit on the MSX screen. So let's take a look at one of the scenes in there. So there's a part in SD you will be locked in this prison. Let's put that on the right, and on the left you can see actually the season and episode and even the minute and second where it was taken from, but it looks really different. So it's modified a lot, and on the left it's 19:6 actually, and on the right it's 4:3. But what is that? I'm also seeing some difference of, and there's some guys on the left which I don't want. So first step is just remove those, move over the wall, because why not? Fill in the walls again. Okay, then I'll need some extra stuff to put in there. Well, what about the skeleton? Oh, so I'll take a completely different season, find the skeleton, cut it out, and put it over there. Why not?
Wow.
And while we're at it, what about the toilet or toilet paper? I don't know. But if you have played this game, you would know you would escape eventually. So I need to look outside eventually. That part, remember it. And I also need a broken wall. Okay. And then put it over there. But how does the character move around? How do you know what to click? I have an overlay with colors in memory. And when you click on your mouse, it just detects which color is beneath that coordinates, figure out which color is it, and everything that's green or having green, like yellow, it's also having green, it means you can walk over there. Other colors are just used to map objects to the script. With what script, you would say? Well, this script. This is part of the script of the scene you just saw. I'm not going to explain all of these script lines, so I'm just taking one which basically says walk to. And what this does is actually, if you click on a certain object, it tells you, in this case the toilet, I think, yeah, it tells you that the character needs to walk over there and position itself, in this case to the right, so like that. So I take this command, change it to be numbers, because he said 80 likes numbers. This is the command length, this is the nesting depth, because it uses nesting. The command is 25 in this case, coordinates, and the direction. So that makes it tokenized assembly code, I would say, or binary even. And if you look at this thing, so it's called 35 prison. This script was written in a total of 873 lines, which includes the text that are there. And in the text format, it doesn't really fit in 16K. So if you convert it to numbers, it would be 11K. So the step in between is just the assembly one, which we compile, and then we compress it just to save disk to 6K. Let's look at the whole game. Ooh. The whole game has 80 scripts in there, which totals to almost a meg of text files. It has 30,000 plus lines, so more, 40,000 dialogue lines, and like a game like Metal Gear actually has his words encoded. This game just has a reference to lines, so it's easier, I think. And objects are stuff like fragments or of samples and also fragments of screen graphics, I would say. So it's more than 7,000 of that. And that's about it about the scripting part. So let's move on to something different topic. And we call it the superscaler. So people that know the Sega had the arcade version of Outrun had a zoom function in there that they called superscaler, so we just stole that term and called it internally like that as well. Let's take another scene. For this scene, we had a problem. Why? Let's first take a look at the sprite or ego, which is not a sprite, we're only using the mouse pointer as a sprite. But let's look at the ego. If I would copy it over, even if I had enough VRAM, if I would put it on the screen, so it's, if I would copy it from VRAM, which I don't, I copied it from ROM, and I put it over there, it's screen 8, so you will be having a problem because screen 8 doesn't really have transparency if you do it quickly. No. So I'm using LNMC, which if you would do it like that, I'm not sure if you can see it, but my black is gone. So that's also a problem, because if you, yeah, it's gone. So what I would be doing is actually making the background purple, but we aren't really doing that, but never mind. Moving on. So we figured out a trick that actually just replaces black with a very dark shade of red, and use black and convert that purple to black before you even copy it. So then you have your sprite, if I would say, on the right way. But what will happen if you walk to that big ass looking door at the end? Does anybody see the problem? So I need scaling. I need to make it smaller. But how to do that? Right? The most easy one is take a lot of version of your same sprite, put it in ROM somewhere, but it's already using a lot of RAM and your ROM won't be happy about it. It will be full very quickly. I've tried it. So what we did is actually, if you scale zoom in a part of the sprite, what we did, this is a sprite of 33 by 79 pixels, and you have RMC. So what you can do is before you transfer to the VRAM, skip a line, skip a pixel actually, skip another one, skip another one, skip another one, and so forth. And you do the same thing when you go to the next line. So draw 2, skip 1. And if you would that display it, it will be scaled to 11 by 26 pixels actually. That's a reduction of 66%. And if you go about skipping pixels creatively, so sometimes 4, sometimes 3, you can get any scaling you want. This is the code that actually is in there. I'm not going to bore you with that. And that is also the end of our presentation.